Hello everyone, welcome back. Today we'll solve problem 24 in DeepML, which is called single neuron. And in case you're wondering, yes, there is a new layout on the website. I'm recording this video just after they launched it. I think they launched it this morning. So it looks pretty cool, and I'm sure it's going to be even better moving forward. That being said, what we're doing in this problem is we're giving a bunch of information. We're given features, labels, which are the true labels of these results of this classification problem. We're giving weights and a bias. And what we have to do with all of that information is output the results of applying a single neuron for a classification problem with a sigmoid activation function to each data point, which outputs these probabilities that we're going to have here, and the mean squared error of this fit, which is this number that we have here. Now, all of these videos are tailored for beginners, so if you had no idea what I just said, don't worry, I'm going to talk about the intuition of the problem before I dive into the code. But before doing that, let me tell you a little bit about how the data is formatted, because it was not as intuitive to me when I saw it, and I think a lot of the ways data is represented may not make sense, especially if you're starting out. So what we're given here as features actually means the data. And so this is a list of lists, and there's three lists. Each of them has two elements. So what this means is that, for example, 0.5, which is the first element of the first list, corresponds to the value of the first observation for the first feature. And -2 here corresponds to the value of the second feature for the second observation. That makes sense, and that's basically the data we're going to be working with. Labels corresponds to what are the actual labels of these data points. So there's three data points, there's three labels. And what this is saying is that the first data point corresponds to class 0, second to class 1, and third to class 0. This is a binary classification problem, so all of the labels are going to be between 0 and 1, either 0 or 1. And this weights here is basically how much you weight each of these features. So there's two features, there's two values of the weights and the bias. So with that being said, let me tell you about the intuition of a neuron. A neuron is basically your building block if you're building a neural network, so it's very important to understand. And afterwards, we're going to dive into the code. In case you're somewhat familiar with neural networks, and if not, that's completely fine. We're going to explain things as we go. You know that in each layer or in each neuron of the network, we're going to have a process like this. So what we're going to do is we're going to have these weights, which is going to be this matrix or vector, depending on what it is you're working with, that is going to be multiplied with what we call here the features or the data, right? And then we're going to add the bias. So if you're thinking about a neural network, each layer is going to have different weights and biases. Here we're looking at a single neuron. So the weight is going to be the same because there's only one layer. So what is happening here? Well, we're passing this thing we call features, which is actually the data, to this layer in which we multiply this by a weight matrix called weights, and then we add a bias. So what this is doing is basically saying, hey, certain features have more or less importance than others. Like for example, if you only had two features and one of the values of the and the value for the first feature on the weight specter was 100, and then the value for the second one was 0, then what that is saying is, hey, I don't care about the second feature. I only care about the first feature for whatever it is I'm trying to do, right? So this weight and this bias are things that are not given and you do not predict ex ante. That is, that you do not come up off the top of your head with which is the optimal weight and bias. Those are things that come up in training. So the whole trick of a neural network is that you grab a lot of these types of neurons and you pass the data along multiple times. And so the model figures out which is the optimal weight and which is the optimal bias. Now, if you've seen my linear regression video or you've had some experience with this, you may notice that if we were to only do this, we would be running into a problem. Consider the following situation, right? Let's say our data had something like that, had a behavior like this, right? And this is not going to be true for the exact problem we're doing. This is just a motivating example. But let's say that we wanted to fit this data just by using this kind of thing that we have here. Well, if we try to make a fit with this transformation that we have here in C corresponds to a linear transformation, right? That there's a lot of other resources that go deeper into why is that what that is true, but it is true. So if you have something of this sort, the only thing you're doing is you're applying linear transformation to the data. And so the only type of prediction you can make is something like this, something linear, right? Because you there's no way you can model nonlinearities just by adjusting a weight matrix and a bias matrix. And so you will have something like this. And it may or may not be a good fit. Right? In this case, it's not a good fit because as we can see, there's a nonlinear behavior in the data. And what's happening here is that we're pretty much ignoring that. We're just saying, hey, a line is the best thing. But in reality, if you just go with a line, you're missing a lot of information. And so whenever you're finishing, after you do this step in a neuron, what comes after is what's called an activation function. And there's a lot of resources that talk about this, but the whole point of an activation function is that it introduces some non-linearity. It allows you to capture this kind of behavior. And so, again, this is not going to work for this type of data, but this was just an example. But the type of activation function you're going to use if you're dealing with a binary classification problem is the sigmoid activation function, which is the one I wrote here. 1 over 1 plus e to the minus c. It's a mouthful, but what this activation function does is it allows your model to capture nonlinearities in the data. So you won't have the problem that we had in the graph on the left. Now, another cool thing about the sigmoid activation function is that it's going to make sure that the outputs of the function, no matter what it is that you're giving it, so long as it's a number, is going to be between 0 and 1. So the return values are going to be between 0 and 1. And someone who's more strict is going to say it's not a closed interval, it's an open interval. I'm just going to put it as closed for now. That's just a math thing that doesn't really matter for now. But all of that is to say that this thing is pretty nice because we can give it whatever data we want and it's going to output a value between 0 and 1. And why is that important? Well, because when you're doing a binary classification problem, you usually want to see whether something belongs in class 0 or class 1. But things are sometimes not all black and white. And what I mean by that is, let's say, for example, we wanted to see, we were given a photo, right? And we wanted to see whether there was a human in the photo, right? And so the way I'm going to train this model is by giving it a lot of images of adult people, adult men and women. And so this model looks at this thing and knows pretty well whether there's a human there, no matter if it's a man or a female. But what happens if we were to, and they're adult, what happens if we were to give them a photo of a child? Well, you may think, obviously, it's going to classify it correctly, but that's not entirely guaranteed. It depends on how the model is built. It depends on how everything goes. Why am I telling you all of this? Well, because what the model is outputting, like what you see if you were to interact through this model with an API or something, is you would see a label, right? You would see the label whether this is 1 for a case where it's a human, and let's say, for example, you pass it the photo of a house that's supposed to be a house, you get 0. But what's happening underneath the hood? What's happening underneath the hood is that this thing, it's outputting a probability, most likely than not. So if you were to use the sigmoid function to decide whether figure represents a person, you would see this as the user, but what would be happening underneath the scenes would be that you're actually getting a probability of your figure being a human or not. So for example, let's say we have these probabilities here, something like this, right? So this function, this sigmoid function that we're getting here, it's going to output a probability, and then eventually depending on which criteria you use, you can map that probability to a value. Intuitively, you would think, oh, if the probability is higher than 0.5, I may go and assign it to a label. That may work depending on certain cases. You may want something that's more stringent or not. But in any case, you're always getting something like this underneath the hood. So going back to the case of a child photo, you may get 0 or 1. It would obviously depend on the model that you're looking at. But I would assure you that underneath the hood, you're getting something like, for example, 0.6540. So what this thing is telling you is, hey, I'm looking at a picture. I'm 65% sure it's human because I wasn't trained with photos of childs, but only with photos of adults. I'm not entirely sure, but given this, I can make a decision. And so depending on your cutoff, you can say either 1 or 0. It all depends on the model. But going back to it, this is the structure of a neuron. You're applying a linear transformation, and then you apply a nonlinear transformation on your data. And if you're working with binary classifications, the binary classification for excellence, usually you're going to use a sigmoid or something that's derived from the sigmoid function. So now that we understand what it is that we have to do and what is happening underneath the scenes, let us talk about the last concept before we dive into the code, which is the fit. So we talked about what's happening underneath the scenes. We're talking about the probabilities, but a question remains, which is how do we know whether this model is good or not? How do we know if we have a good fit? And so let's get back to this. So the way you would know if you have a good fit or not would be by estimating how much your model deviated from reality. So again, I talked about how you get some probabilities and based on those probabilities, you assign a label. We're going to say that we're going to have a vector that's going to be called predicted, right? And we're also going to have another vector that's going to be called true. So what these are supposed to represent is that this is what the model tells you, and this is what is in reality. And ideally, what we would want is for predicted to be very, very, well, ideally, we would want them to be equal. We would want predicted to be equal to true. Now, that's most likely than not, it's never going to happen, but we can at least get somewhat close to this thing. And so there's multiple ways in which you can say that you have a good or bad fit. One way to assess the goodness of fit is by using a metric called mean squared error. And if you've seen the videos on linear regression, you've seen this thing. Basically, what we're doing here is we're taking an average of how much the predicted value, how much the predicted value, I'm going to call pred because my mouse is going crazy, differs from the true value. So for each observation, how much are we differing? And we're taking the square of that. That's for smoothness. Doesn't matter for this video, but basically what we're doing is we're saying, hey, how different it is on a observation by observation basis. So with all of that said, that's exactly what's happening underneath the scenes. Now, if you were working with a neural network, you wouldn't calculate this fit for every neuron because some of them are just intermediate steps and don't tell you anything about the output. But once you get to the end of the neural network, you're going to assess your fit, and based on that fit, you're going to revise your values of the weight and the bias. So with that being said, I know this was a long explanation, but it helps you get an idea of what it is that we're doing underneath the scenes. And now we can go dive into the. Okay, we're back. So what we're going to do first is we're going to write the code skeleton. So first we're going to do the linear step of getting C. Afterwards, we're going to apply, I'm going to apply the activation function. And afterwards, we're going to calculate the goodness of fit. So all of that is going to happen here. Now, there's multiple ways you can do this. I'm going to follow the official solution because I think it's very straightforward. I was thinking about doing like a naive way without like fancy Python tricks, but I realized that the actual solution is pretty good and it's going to make your life better. There's no reason why you shouldn't use this. So we're going to define a vector for the probabilities, a list, and then we're going to iterate for each feature vector in features. So what we're doing here is we're iterating on each of these lists here. It's basically iterating on each data point. So first we're going to get what I said. It's going to be the linear step. This is getting C. And there's multiple ways you can do this, but again, because we're doing it on an observation by observation basis, what we want to do is get W times feature plus the bias. So we remember that this is within a sum because you were summing over the features. So we're saying weight times feature for weight feature in sub weight feature vector. I'm going to explain that in a second, plus bias, which is the thing that we talked about. Okay, so what's happening here? Well, remember when you use the SIP function, what you're doing is you're combining elements on an element by element basis. So the first time we go through here, this is going to be our feature vector. These are going to be the weights. And what we're doing is we're combining 0.5 and 0.7. That's going to be a list. That's going to be merged with one another. And 1 is going to be in line with minus 0.4. So when we're doing this, we're ensuring that this weight is multiplying this feature. And it's going to be a one-to-one mapping. So after we have the C, the next step is to get the activation function, which is the sigmoid. And there's multiple ways you can implement the sigmoid function. There's one that's not numerically stable, but I think this one is the correct one. And we just apply this sigmoid function that we talk about, 1 over 1 plus the exponential of minus C. Afterwards, we're going to add this newly calculated probability to the probabilities list. And we're going to round it 4 decimals because the problem is asking us to do so. Okay, so we do that and we get the probabilities, all of the probabilities together. Now that we have all of the probabilities, after we finish that loop, what we're going to do is calculate the goodness of fit. And what is the goodness of fit? Well, the goodness of fit is this mean squared error that we were talking about. So we have to first multiply this by 1 over n, where n is the number of observations, which is the same as the number of labels. And we're going to multiply this by the sum of probability minus label squared. Remember, we're taking the square. If you're wondering why, there's a lot of very interesting videos that talk about that more in depth, especially the one in linear regression. But for now, let's just assume that this is how it works. And we're doing the same SIP trick. So we're making sure that the corresponding probability, which is going to be a list of the same shape as this, is going to be mapped to the label here. And once we do that, we're going to have the mean squared error. We just want to make sure that it's rounded to 4 decimals. This is just to ensure numerical stability and that there's no discrepancies because of floating point arithmetic. So with that in mind, that's the code. It's very straightforward, as you can see. And once we run it, this thing should work. And oops, we made a mistake. Name weight is not defined. Oh, okay. Well, that's why it's important to always read your code. This kind of thing happens way more than I would like to admit. And there we go. Wow, this is a very neat screen. I had not submitted any problems since they made the new layout, but it works. Anyway, this is the solution. I hope that this was helpful for you. As always, I really like to go in depth explaining the concepts to beginners. And as I said, this is a great problem because building a neural, if you can do this, you can build a neural network. You're pretty much halfway there because the only thing you have to do is like stack some blocks of this and worry about the back propagation, but the rest of it is very straightforward. So thank you again for your attention, and I hope to see you in the next video.